some concern, or it should be of some concern to you, is that there's an exam on Thursday, right? All right, and I promised you that we were going to go over some problems, some relevant problems, and we're going to have to finish up some material. So I think we're going to do that. We also have to talk about where we are in terms of those projects, right? And Bernard, since you set it up, I'm going to ask you what the status is of your group's project.
Spring year.
Or maybe we should turn the camera in your direction. All right, but seriously, I think at this point every group should have an organization that they are working with. So let's make sure.
Professor Powell,
Yes.
those figures and tables that you gave to me last week, can those stay up online? Is that okay? Or they're like
How long do you want them to stay?
it doesn't matter. I can send the link to everybody right now.
All right. That's fine with me.
Okay.
But we can't keep it up interminably.
Okay.
Let's we got to bring it down soon.
I need a list of the functions.
We need better background, I think.
Modules that you did. Okay. So which two did you do? Well, you know
I haven't spoken to Kevin.
Okay.
He's a good man, right?
You're supposed to listen here.
Rainier, Kevin is a good man. Is that right?
For support.
For the web.
Oh, yeah.
All right.
Function B. There was a.
Have you talked to him about what we're doing?
Yeah.
Yes.
All right. So he's aware of it, and he's willing to do it.
How
When is he normally
Like an
around?
example of it.
You know what? When he has class?
Yeah, I need. Because did you see there was a Word document with boxes connected?
On Tuesday, Thursday? Wednesday?
Yeah.
We gotta
I'm going to
make
be
one.
around. I have office hours tomorrow. Are you going to
For
see
each of
him?
the X's,
Yeah, I can.
Yeah.
each X
I
on the
have
chart
office
should
hours
have.
tomorrow. I'll be around probably, I don't know, roughly 1 to 4.
Okay, other.
You don't have to make that. I just need
Around.
to.
I'll try to make it. I've got to make up your exams too. I know what I'm
And
going to do, but I
if you look at it, once you look at it, you'll figure it out.
Alright. Hold on.
Just trying to explain what's going on, dude.
as long as you have on the tube here, we've got to show something worthwhile. I don't. How about that as background? Okay. All right, so let's going through the groups here very quickly. George, your shop here, the leader.
Yes.
Steve, Irving, Monica. What company, what organization are you going to be working with?
We're working with Business Data Links.
Business Data Links. Have you spoken to anybody there yet?
Yeah.
Okay. And we're willing to. All right. Chris, Joseph, Lee, Mike, Susan, I don't see Mike, but Susan, you're here. Any, Chris, what did you folks come up with? Which one? Big Head?
Yeah.
Big Head Design. Okay. Have you spoken with anybody yet? Good. And how about your group?
Right.
How about your group? What are
We're going to work with a Seacliff Homeowners Association.
Seacliff Homeowners Association?
I know who we're working with now.
Where have I heard that? Somewhere, like an echo. All right, William, Derek, Luke, Eric, Clark. How about you guys?
DirecTV.
Ah, big one. Big one. All right, good.
We're hoping. I don't know for sure.
Hopefully they come through though.
Derek. I've talked to him.
Very nice. Okay, so it's nice to have at least one company that we all have heard of.
Like that.
All right, how about the hands-on? How's that going? Have you selected anything yet? Tell you what, Thursday's the exam. How about Tuesday next week? We find a project to work. All right, any questions about what we did last time? We've been going through this free space, and we're almost finished. There are a couple of things that I want to mention about it before we get to these problems. We may have done everything in this chapter. Okay, we had ended with this. Now there are different kinds of fading. I'm not going to go through the technical stuff. We look at some of the tables and figures, and I think we saw some of that before. What is the main idea behind fading now? The mic is over there. But what is the main idea behind fading? Remember? What is fading?
Isn't it like the slow, I guess, fading of the signal as the farther out you go?
Well, no, that's loss. Figure 513. Yeah, this is a pretty good. The idea is that because of any number of some of those impairments that we talked about, like multipath, reflections and refractions and all that, scattering, all that stuff, the signal strength, the received signal strength, is not uniform. You'd like it to see, as the distance went out, as it increases, be going, down like this. But it doesn't really do that because of these received signals and the delays and other kinds of things. So it's not uniform. So what we see is, this shows you the amplitude in dBm versus the position. It varies. It goes up, it goes down, it goes up, it goes down. And it can go up and down rapidly, which is fast fading. This is in an urban mobile environment, mobile buildings. Or it can do it slowly, different kinds of fading. But that's the basic idea. Speaking of which, Did you know that in New York City now, the Empire State Building is no longer the highest structure?
Yeah, they just,
Yeah, they just passed it by.
they just passed it, yeah,
Right.
during construction, right?
Right. Yeah, the One World Trade Center is now higher. And they haven't completed the building yet, but I think for what they've built so far, it's now higher than the Empire State Building. But you know, in a city like New York with all those high buildings, there's plenty of these fading kinds of effects. At the top of the Holiday Inn London Kensington Forum, where we held WTS, the people, the salespeople, took Kathleen Buttigieg in the dean's office and up to the top floor, and they took us up on the roof. All the way in the distance, you could see a tremendous building that they're building called the Shard. It should be ready around Olympic time, but it's comparable in size with some of the tallest buildings in New York City. So the London skyline has changed tremendously. They also have, I don't know if you're familiar with it, a large Ferris wheel called the Eye. Have you heard about that?
In London?
Yeah, in London. They built this a few years ago. Yeah, I've never been up, but apparently you get a tremendous view of London.
How much does it cost?
The Eye?
Yeah.
To get on it?
Mm-hmm. No.
Well, you'd like to go?
Yeah.
It'd be nice, eh? And then now you go up to the top of the Shard too when it's built. Yeah, so it's really, and they've got this I don't know, they call it it's like a pickle. It's a building built like a pickle or a cucumber, right?
Oh, interesting.
They gave it some name like that. But they're, you know, it's a lot different than a lot of new buildings going up over the past several years. All right, in any event, so that's fading, and you know, there are some technical kinds of things, and, formulas, and they've done a lot of different kinds of calculations to look at fading, and models built on fading, but we don't have to go through that. Going back to here. Going back to here. So now the question is, how do you overcome some of these problems? And there are three error compensation mechanisms that are described in the overheads and in the book. And the book, as I mentioned, the library may have a copy if you want to purchase a copy, use a copy. And they are forward error correction, adaptive equalization, and diversity techniques. So let's talk about it. This one you may have seen before. Anybody hear about forward error correction? Like in CIS427? Don't remember that? Remember, what is error correction? Remember error correction?
It's when like the data has kind of like a checksum, so it can like determine whether
Yeah, you're partially there. Remember, the idea is that there are two kinds of processes. One process dealing with errors is the detection of an error. Right? And then the next thing is to correct the error. So first you have to be able to detect the error to find out if there is an error, and then you want to be able to correct it. In terms of detecting the error, that's where the checksum comes in. Right? And they add all these different codes. You remember that? CRC and that basically parity checking, longitudinal, all these fancy things. That deals with error detection. And then you get into the whole question of correction. And once you detect the error, how do you actually correct it? And there are, if you recall, going back to 307, and you may have discussed this in 347 too. Remember automatic repeat request and stop and wait and all that kind of stuff? Yeah, what is that about? Remember? One thing you can do is the stop and wait procedure. Remember, where you wait for an acknowledgement, and if there is a negative acknowledgement because there's an error, then you retransmit. Is that one? And there's that stop and wait error control, and then there's this go back in. Remember that one where you go back a certain number of frames and then retransmit, and then selective repeat, where when you find out which particular frame is an error, then you retransmit the frame. But those are all error correction kinds of techniques. The problem with them is what? Think about it. Think about a link that's a long link, like a space shuttle or a spacecraft going out into outer space. Think about communication between the Earth and the spacecraft. That can be a very, very long distance. And even the signal is going to travel at what speed as it goes through space? That's a number you should remember. Yeah, 3 times 10 to the 8 meters per second, or 186,200 miles per second. It sounds like it's fast, but if you're dealing with light years, that's actually not very fast at all. So if you're going to wait for an acknowledgement and then correct, because you now know what the error is, and retransmit, by that time we're all very old, if we're around at all, because these are very, very, very long distances. So you can't do that. You've got to use a procedure that has built-in intelligence, where the receiver can actually correct the error based upon what it receives, not request a retransmission. And that's what forward error correction is all about. They call that forward error correction, meaning that the receiver can correct. Again, it's complicated. It's more bits, more logic, all of that kind of stuff. But that's the basic idea. So that's forward error correction. Let's see if we can talk about it. Yeah, the transmitter adds error correcting code to the data block. The code is a function of the data bits. The receiver calculates the error correcting code from the incoming data bit. If the calculated code matches the incoming code, no error occurred. If the error correcting codes don't match, the receiver attempts to determine the bits in error code. So the receiver does it. I mean, it's up to the receiver to correct the error. Okay, that's forward error. So that's one possible scheme. Adaptive equalization. Let's talk about that one. Now, I think you know what an equalizer is, those of you that are familiar, for example, with stereo. Anybody have a graphics equalizer in a stereo system? This is the thing where we adjust the amplitude of the signal power at any given frequency. Like if you like booming bass, you turn up the bass and whatever it is. But that's adaptive equalization. I think I mentioned that. One of my instructors when I was an undergraduate at MIT was Amar Bose, who later went on became very wealthy and very famous for the Bose speaker system. He actually taught the introductory electrical engineering class that I took, and he was responsible for for my majoring in electrical engineering because he was such a good instructor. Had I done it all over again, and had I had a better instructor for economics, I probably would have done economics. But that's the way things work. But in any event, Bose was very good. And he taught at an excellent class. And I saw him a little bit after that. That was after I'd come out here. I was working on my PhD. And to Bose, I'm teaching your course. Actually, I was at that point. I was teaching at USC. I'm teaching your course at USC. And he was very, very happy to see it all. And I said, in addition to that, I'm using your speakers. Now, he came out with a set of direct reflecting speakers, the old Bose 901s. I don't know if anybody's familiar with that. Well, it's a little diagram. The basic idea is, you have a room, and you've got these speakers. They look like this. Full range speaker over here, and then there are 4 full range speakers here and 4 full range speakers here. And ideally, you're supposed to put the speaker on the outside. In my house, I don't have room right now. It's actually on the inside. But it's supposed to be kind of like on the outside. And the idea is that the sound is direct, but it also reflects. All over the place. And it was his contention that this is much better than quadraphonic or surround sound or all the other schemes that they've got. It's the most realistic kind of thing when you're in a concert hall. It's more like this than anything else. So they sold. I bought a pair of the original 901s. They've gone through different iterations, and so he was very, very happy to hear about it. And he made a lot of money, as you know, from that. But with this 901 speaker set, there is a little box, an electronic box, called an equalizer. And the idea is that because of the way the speaker is wrapped up in the box, and with a cover, there's some mesh or something in front of it. It really adds some impairment to the sound. And this equalizer is supposed to overcome that impairment. And you can play with the knobs, you can do a number of different things with it, much as you can with the graphics equalizer. So the point is that these equalizers exist. And they change the frequency response, and they can do other kinds of things too. The adaptive nature means that it learns over time. And it learns what the impairment is, and it can change. It can change the receiver and receiving mechanism to overcome this kind of impairment. Okay, that's adaptive equalization. Take a look here. All right, it's a little bit more complicated. He talks about what it is, but basically that's it. Can be applied to transmissions that carry analog or digital information, analog voice or video, digital data, digital voice or video. It's used to combat intersymbol interference. It involves gathering dispersed symbol energy back into its original time interval. And the techniques include lumped analog circuits and sophisticated digital signal processing. It can get very, very complex. The 901 doesn't have any feedback or anything. You just set it. That's the same thing with the graphics equalizer. You can purchase, if you want to increase the boom in your musical bass. But the more complicated ones have this kind of feedback to overcome this kind of impairment. Okay, that's adaptive equalization. The last one we're going to talk about is diversity technique. Okay, diversity. And the idea here is that rather than receiving or transmitting one signal, you transmit copies. But the copies may not be exact copies, they may be done in different ways. So let's look at some of them. It's based on the fact that individual channels experience independent fading events. And there are such things as space diversity, techniques involving physical transmission paths, frequency diversity, where the signal is spread out over a larger frequency bandwidth, or carried in multiple frequency carriers, and time diversity, techniques aimed at spreading the data. Let's think about this. It's really very simple. A lot easier to understand than it's written here. You may have seen in cars. Remember we said that there's this fading, and the fading is varies over distance, over position. That's a better word than distance. At the front of the car, the signal can actually be received better than at the rear of the car, right? Because this change, according to the fast fading that we saw, this change in position can be very, very small in order to get a significant kind of fading. So it would seem to make sense that you should put an antenna up in the front of the car and one in the back. And each one is picking up the signal, right? And each gets a copy of the signal, at least where it's located. And then it's a question of what to do with the received information. You now have two versions of that information. One thing you can do is you can average, right, what you get. Another thing you can do is you can take a weighted average. It gets more complicated. But a very simple approach is just to take an average. And average it out. And that, by doing it that way, you can increase the reliability of the reception. That is a space diversity technique. You can do this with different antennas, any number of things. It can be done on a satellite, it can be done on a mobile, I talked about an automobile, a vehicle, all kinds of things that you can do. It's called space diversity because you're using space to receive it. Okay. A separate antenna, two separate antennas, different in space and position. Frequency diversity is a different kind of thing. One common thing you can do with this is you can send the signal, transmit the signal at two different frequencies. Same signal, same information, but at two different frequencies. That way, if one frequency is corrupted, is impaired for one reason or another, you hope that the second frequency is not. And again, you do the same thing. You can take an average or however you want to do this. Or you can look at which is the higher signal strength of the receiver and take that. So that's what your signal is going to do. You can look at that approach as well. It doesn't necessarily have to be an average, looking at it on an average. So that's frequency. They talk about spreading it out over a larger frequency, as you might have in frequency spread spectrum. We'll get into that. But certainly looking at it being carried on multiple frequency carriers makes sense. Time diversity is just what you think it would be. Rather than sending a signal at one time instance only, you can send it at one instant and then another instant, and keep going. So the copies are transmitted at different times. And you can use the same approach. You could look at which signal is stronger. You could take an average, whatever. Diversity means you're looking at redundancy in transmission and reception. Okay, everybody got the idea? Diversity. Now, in none of these are you really increasing the signal strength. Okay? You're doing these kinds of things without having to increase the signal strength. Because remember, you really don't want to increase the signal strength. We said that you can always, if you can, it's a nice thing to do because you can increase the signal to noise ratio. But the downside certainly is that there's more power necessary. You don't want to use it. You'd rather minimize power consumption and maximize power consumption. And these methods do not require you to increase the signal. So they're nice. They're nice for me. They do. They can correct errors fairly reasonably well. Okay. So that's pretty much your limit. Anybody have any questions with these overheads? Let's present it. All right, let's get back to then our link that we looked at the other day. Remember I drew the block diagram on the board for you. Why don't you tell me what the parts of the link are and how we go about doing the analysis, because we're going to make some enhancements to it coming up. Okay, what are the parts of the link? Remember in that block diagram, what are the different blocks? Where do you start off? Remember, I said you can bring a formula sheet, but that's just it. Just with some formulas on and a calculator. I don't want you to use a computer, just a simple little calculator. But you have to know what's on the formula, so you have to understand how to use the formula. And really, honestly, I don't think the formulas are the best way of approaching solving these problems. So what do you do? What do you do? Don't raise your hands at once. Susan, let's start with you. Oh, you were here. I know that. I remember that very well. What do you do? I mean, where do you begin this?
With the transmitter?
All right, good. That's exactly it. I think a good way to think about this is remember the Shannon general model of communication. Remember that from 307? It's a very important part of telecommunication. You learn about it in 307. What is the general model of communication, according to Claude Shannon? Remember, there's a source that wants to send a message, and the message is encoded by a transmitter via a signal, which is transmitted over a channel, and a noise is introduced into the process in the channel. So the receiver is going to receive the signal and the noise, and then the receiver is going to try to detect what the original message was, or decode from the signal and noise. Decode the received signal and noise, received signal, and decode it and hope, you hope you get the original signal back. The original message, I should say, the original message. So that's the general model of communication according to Bush and Father's information. All right. Now you can build on that. I mean, that's really what we have here. Because we have, think of the transmitter, and Susan just talked about it. And then we have a receiver. And then we've got a channel. Except it's actually a link. And we're looking at the different parts. So Susan, you started off in the right place with the transmitter. And the transmitter is transmitting okay, so what's next in our block diagram? Somebody else want to suggest the next block in this?
You say coding?
No, not coding in this place. We're not talking really about coding. We're talking about the way over the link, we're looking at the reception of the signal. Now, it's pretty clear that there'll be noise and all that, and we're going to get into that later on. But in terms of the coding, we're really, at this point, not worried about it. But we just want to receive the signal and look at what we receive, and look at the noise, and compare the signal to the noise. Now, the signal that's transmitted from the transmitter is going over a transmission line, right? And what happens as it goes over the transmission line? It's going to what? In general, it's going to experience loss, right? And, a transmission line can be, for example, it could be copper, it could be optical fiber, it could be wireless for all we know, but it's some kind of transmission line. All right, but it's going to experience some kind of loss in general. And the next block after the transmission line is what? In this
Receiver?
no, an antenna. Remember, there's a transmitting antenna. It's connected to the transmitting antenna, and that transmitting antenna is going to transmit a signal, a wireless signal, through free space, and that antenna has a gain associated. Remember, the gain is the direction. So you do the gain in a certain direction relative to the omnidirectional, the isotropic antenna. Okay. What's the next block after we leave the antenna?
Free space.
Free space. Okay. Then we're going out and over free space. And it could be a long distance, it could be a shorter distance. It could be between a garage door opener and a receiver. It could be from the Earth to the satellite or out the spacecraft. And we know that there's loss associated with free space. And then it's received, right, by what? Another antenna. Okay, and that antenna has a gain associated with it. And then what's the next step after the antenna receives the signal? It's going to
The transmitting line.
put it out over a transmission line. There will be more loss. And then finally, it's going to be received at the destination. Okay, we're not really worrying about coding or anything. But that's the basic process. And the noise can be introduced anywhere along the way. And we looked at various kinds of noise. The most common one that we saw was the thermal noise. All right, so that means that the at the far end, the end of that transmission line, destination, really the receiver. When I think at the receiver, because we've got the receiving antenna and then the transmission line. At the receiver, there's going to be a combination of signal based upon the original transmitted signal and whatever happens to it, and the noise that has been introduced in the process. Now, so that's what we did last time. We looked at that. We'll look at some more examples. But let's think a little bit more about this. Let's say we really want to design a link also. I mean, it's one thing just to analyze it, but it's not sufficient. You want to be able to design the link too. So in designing the link, we want to do it in such a way that the received signal is going to be strong enough so that we can detect whatever it is. Not in terms of coding, but in terms of utilizing it. Say for voice, it's a voice signal, or video, or data, whatever. And there are different properties. We talked about how noise can corrupt the signal. And it can corrupt some signals more than other signals. So for that reason, you may want higher signal strength or higher signal-to-noise ratio based upon the specific application that you're dealing with. So for example, noise, maybe 10 dB. Signal-to-noise ratio, speech, 10 dB. Video, 30, 40 dB. So depending upon how complicated the information is, it may require a higher signal-to-noise ratio. So there is a minimum required signal-to-noise ratio at the receiver based upon the application. So you know that. Let's say it happens to be 30 dB. So you know that at the end of your link, you're going to require 30 dB signal-to-noise ratio. So that means the receiver at the far end has to have 30 dB signal-to-noise ratio when it receives the signal plus the noise. So what are the implications of that with respect to the design of the link? Now, what do we have to play with here in terms of our link? As designers, what can we do? Clearly, one thing you can do is you can move the antennas forward and back, but that may not always be realistic. For example, with satellite, we know that there's a specific. It's a GEO satellite. GEO is up there, 22,300 miles. You're on the Earth. There's not much you can do about moving the antenna. What other things can you do?
Choose the right connections.
All right, how do you mean that exactly?
Like from the transmission to the antenna, like choose the best one.
Transmitted. Okay. I think what you're talking about is line loss, right? One thing we can do is we can try to use a medium that is less lossy. That would seem to make sense. You want to increase the signal-to-noise ratio. We know that a less lossy transmission medium, both at the receiver and the transmitter, can do that. Is there anything else we can do? Clearly, you can increase the transmitter power, but that's not always something that's desirable. We talked about that. For example, if you have a small cell phone, you don't need a whole lot of power. How about the antennas? Is there anything we can do with the antennas? Increasing the gain. How can you increase the gain of the antennas?
Have more antennas.
Well, so much more.
That's not
How about the area? Remember we said the effective area? The gain. We want to increase the gain of the antennas, and one way of doing it is to increase the effective area of the antenna. All right. So there are some things that we can do. Depending upon the application that we've got, the situation. Some are easier to do than others. And the objective then is to have that received signal-to-noise ratio be in excess of the required signal-to-noise ratio. This sounds very similar to what you do in accounting. Accounting, I don't really get into accounting. But if you think about it in business, the objective is not to lose money. The objective is to be profitable. So if you know what your costs are, right, what you want to do is you want to generate revenues in excess of your cost. Right? And if you know what the profit, what your required profitability should be, then you know how much in excess of the cost. I mean, you have just so much to play with. You can lower cost, you can increase revenues, but there's not much more you can do. I mean, you can play around with taxes, and things like that, but that's more chemical. But basically, it revolves around revenues and expenses, right, in determining profits. It's the same thing here. You've got the required signal-to-noise ratio, you have the received signal-to-noise ratio, and you have the difference between the two. Now, in accounting, you call this a budget. Remember, you want a budget. You make sure that you've got enough money to go forward. WTF, you want to have enough money, enough surplus for future companies. Same thing in here, in this link budget. You want to have enough margin between the required signal-to-noise ratio and the received signal-to-noise ratio. So that's called link margin. Link margin. Okay. The difference between the received signal-to-noise ratio, the actual received signal-to-noise ratio, and the required signal-to-noise ratio is called the link margin. The last thing which is sometimes a measure. You know that there are different measures of how well you're performing in a business. What would be some typical kinds of measures of how well you're performing in business?
In business?
Yeah. How do you know whether or not you're performing?
Market share?
Which one?
Market share?
I'm sorry?
Market share?
Market share. All right, market share can be a measure.
Revenue.
Well, that's an absolute thing. How about in terms of a ratio? Market share is a ratio, but I'm thinking now in terms of, market share doesn't actually show anything on the profit and loss statement. Right?
Return on investment?
How long you keep
Yeah, now we're getting closer. Yeah, something like that. Like operating margin, return on investment. These are ratios.
Yeah.
And they give you an idea of how well you're performing, return on assets, et cetera. Well, there is something in telecommunications too, wireless communications. So a measure of how well you're doing. It's called spectral efficiency. Spectral efficiency. And what spectral efficiency is it's the data rate that you can achieve divided by the bandwidth necessary to achieve that data. The data rate you can achieve divided by the bandwidth necessary to achieve that data. So let's think about it. I mean, it kind of makes sense. All things being equal, we said that bandwidth is scarce. All things being equal, you want to conserve bandwidth, right? You want to minimize the amount of bandwidth that's necessary to use. So if this ratio is data rate divided by bandwidth, and bandwidth is decreasing, the ratio is increasing, you're becoming more efficient in your use of spectrum. Seems to make sense, right? All right, let's look at the numerator. The numerator is data rate. Let's now fix the bandwidth, but increase the data rate. Well, that's good too. That means you're using, you can get higher, more data going through your amount of spectrum, and that's good. So that would be desirable as well. That would increase the spectral efficiency. So it seems to make sense that spectral efficiency, data rate divided by bandwidth, might be a pretty good measure of how well you're using your spectrum, how efficient you are in your use of spectrum, at least in terms of the transmission. Everybody with me? All right, now we're ready for the problem. All right, let's do this. We've got, what, about an hour here? The objective is to go over some of these problems. And the objective is not for me to do all the talking. The objective is for you, actually, to do the talking. My talking is going to be involved in giving you the question. Your talking is going to be involved in answering the question. So here's the problem. And then there are 5 parts to this problem. Right? So why don't you write some things down? What we're looking at now is a GSM cellular radio link. Now GSM, I think you're all familiar with. It's a second generation cellular standard. They've gone past that. But in many places in the world, they're still using GSM. So let's consider a GSM cellular radio link. And let's call it A, capital A. Consider a GSM cellular radio link, capital A, between a mobile station at rest, and a fixed base station. Consider a GSM cellular radio link A, capital A, between a mobile station at rest and a fixed base station. Assume that the distance between the 2 stations is 10 kilometers. Assume that the distance between the 2 stations is 10 kilometers. And the carrier frequency is 905 megahertz. From the mobile to the base station, carrier frequency is 905 megahertz from the mobile to the base station, and 950 megahertz from the base station to the mobile. 905 megahertz from the mobile to the base station, and 950 megahertz from the base station to the mobile. Assume that the mobile and base station antennas, are used for both transmission and reception. And their gains are 20 dB and 40 dB respectively. I'm going to repeat that. Assume that the mobile and base station antennas are used for both transmission and reception, and their gains are 20 dB and 40 dB respectively. Assume the power of the mobile and base station transmitters. Assume the power of the mobile and base station transmitters are 4 watts and 50 watts respectively. Assume that the signal energy at the base station transmitter / receiver, assume that the signal energy at the base station transmitter / receiver is twice that at the base station antenna. Assume that the signal energy at the base station transmitter / receiver is twice that at the base station antenna. Okay, everybody got all that?
Can you read the last sentence?
All right, let me read the whole thing. Consider a GSM cellular radio link, capital A, between a mobile station at rest and a fixed base station. Assume that the distance between the 2 stations is 10 kilometers and the carrier frequency is 905 megahertz from the mobile to the base station and 950 megahertz from the base station to the mobile. Assume that the mobile and base station antennas are used for both transmission and reception. and their gains are 20 dB and 40 dB respectively. Assume the power of the mobile and base station transmitters are 4 watts and 50 watts respectively. Assume that the signal energy at the base station transmitter/receiver is twice that at the base station antenna. All right. Right now, know what's going on. Think in your mind what's happening here.
Last question. Can you usually assume the distance between two stations
Is 10 kilometers, and the carrier frequency is 905 megahertz. The mobile to the base station are 950 megahertz from the base station. All right, so that's the problem statement. Now we have the first question in the problem. And that's what there's 5 of these. And if you know this, you'll be in good shape for the midterm. All right? At least this part of it. Before I forget, let's talk about what else is going to be on the because we did a lot more than that. Remember, we started off, we talked about the wireless telecommunications industry system, and we looked at the different parts of it. We looked, for example, at regulation. We talked about the ITU, spectrum management. We looked at spectrum management. We looked at the ITU, the FCC, the NTIA. We looked at allocation. We looked at allotment. We looked at assignment. Then we kind of got into, we talked a little bit about some of the technology, looked at waves. We looked at antenna. We talked about DB, DBW, DBM. All the kind of stuff that we saw here in these overheads. We looked at different kinds of noise, impairments. So don't think. I don't want you to think that it's all these questions or these calculations. The calculations are just part of the midterm. Anybody have any questions about the things I just said? Because that is a substantial part of the midterm. So.
Those things you just mentioned right now?
What? The things that I just mentioned? Yeah, that's on the midterm.
So is this like multiple choice for the answer?
No, it's not going to be any multiple choice.
For an answer?
Yeah, I mean, they're not long things. But you're going to have to answer. You have to know what these things are.
PowerPoint?
What about PowerPoint?
Is there serious?
No, this material was not on the PowerPoints. This is what we discussed in class at the beginning of the quarters. We didn't really get to the PowerPoints until a little bit later on. You remember that spectral chart? And I said you should be familiar with the different parts of the spectrum. This gives you an opportunity to show that you are familiar with the different parts of the spectrum. Yeah, I saw a hand. Yeah.
Could you quickly repeat what you just said?
About what?
Before the...
About the different part, about the exam?
So you said equations.
Yeah, besides the equation? Yeah, there's a whole lot of stuff that we covered. We just picked up, we did this was only about a week or two ago. There's all that material at the beginning of the quarter.
I tried to look for the spectrum chart, but I can't find it. Do I just somehow Google search it to find it?
Yeah. Was anybody else, was anybody able to find the spectrum chart? Yeah, how do you do it? Through the FCC or the NTIA?
I remember, but when you went to that page, we followed you
right
to that page.
You're talking about the US frequency allocation chart?
Yeah.
This Google spectrum.
Yeah.
The first thing that popped up.
I think I looked it up. I just did a search on the FCC website.
Just Google FCC spectrum chart.
Yeah, that should do it, FCC spectrum. Or NTIA.
that's your studio specifically.
And then, but yeah, I mean, if you look it up, you'll find it. What do I recommend? What do I suggest you know? Well, the major parts of it, not everything equal.
What is considered a major part of it?
Where is AM radio? Where is FM radio?
Okay.
Where is TV broadcasting? Where is satellite? Are you familiar with
Can you
all
repeat
those
that?
frequencies?
Can you repeat that? AM, FM, radio, what else?
I can't, everything that we talked about. And not only that, you should be familiar where microwave is, where the radio part of the spectrum is, where ultraviolet is, where light. This is actually stuff that you did in 307.
We did not do this.
You didn't, no, you did it. Yeah, I'm sure you did.
We did.
In every textbook they have it.
That's why we're asking you, because we didn't cover it.
Really?
Yeah.
Which textbook did you use?
William something?
Stalin?
It's the white one with, is it, what was it called?
And you didn't have it in there?
Well, we didn't cover it. It might have had it in there.
Oh,
Yeah, we didn't cover it.
all right. Well, now we're covering it. But,
So that's why we're asking you questions.
okay.
Yeah.
It's a shame. You should have had it. There we go. It's figure 210. This is the same thing that was in your books, in 307. But as I said, there's more detail in the other one. It's just the basic. It shows you a lot.
This one and the other one is, way,
This is not that complicated, really.
This isn't that complicated.
You already know this. No, this really
When you
should know.
compare it to the one online.
Yeah, the other one's a lot more detailed. But certainly you ought to know this.
I mean, I think I recognize that, actually. But the other one was like, oh.
All right, no, I understand. I don't expect you to memorize it. But I want you to become familiar with the different parts of it.
Anyway, we can get
And you're telling me that in 307 they never went over this? It's in the book.
It wasn't.
Stallings has it in his book.
I mean, it wasn't good, but the thing is, it wasn't taught, and it wasn't that, knowing it that much wasn't that important.
All right.
We really learned about just
like over the ATM.
like multiplexing and yeah, exactly.
All right. That's important too. But this is also.
Is there any way we can get a PDF?
Yeah, what?
Get that PDF file?
You have it.
Do we?
I sent it.
Yeah, we just got it.
You got it already.
I didn't realize.
It's figure 210. All right. All right, so does that answer your question?
It helps us.
All right, good.
Makes it a little less.
All right, so let's get back to this. So here's the question. That's the problem statement. here's the question mark. Compare cellular radio link A. Compare cellular radio link A, capital A, given above. I just gave it to you. Compare that with an AMPS, AMPS. AMPS. That's a first generation cellular standard. AMPS, Advanced Mobile Phone System. But compare that, given above, with an AMPS cellular radio link B with an 830 megahertz carrier frequency. Compare that with an 830 megahertz carrier frequency from mobile to base station, and an 870 megahertz carrier frequency from base station to mobile. Which of the two cellular radio links has the longer mobile to base station carrier wavelength? How much longer is it? Which of the two cellular radio links has the longer mobile to base station carrier wavelength? And how much longer is it? Now, we've got about a half an hour. It should give us time to go through these problems.
Can you repeat the whole thing?
Compare cellular radio link capital A given above with an AMPS, AMPS, cellular radio link B with an 830 megahertz carrier frequency from mobile to base station and an 870 megahertz carrier frequency from base station to mobile. You got that so far?
That last thing. Sorry,
And an 870 megahertz carrier frequency from base station to mobile. So now there are two questions about that. Which of the two cellular radio links has the longer mobile to base station carrier wavelength? And how much longer is it? Which of the two cellular radio links has the longer mobile to base station carrier wavelength? How much longer is it? All right, that's question one. I think so that we make sure we have everything here. I don't want to run out of time. Let's do question two. Why don't you write it down? 2, ignoring all losses, except the losses described above. Calculate the signal, in parentheses, carrier. They use that term too. Calculate the signal, in parentheses, carrier, C-A-R-R-I-E-R, carrier, close parentheses. Level capital C at the mobile in both dBW and watts. Let me repeat this. Ignoring all losses except the losses described above, calculate the signal, parenthesis, carrier, level C at the mobile in both dBW and watts. Okay, everybody got that? Let's do 3. Write this one down. Assume that the mobile receiver has an effective noise temperature. Assume that the mobile receiver has an effective noise temperature of 180 Kelvin, 180 K, or 180 degrees K, if you like that. Capital K. And a 1 megahertz bandwidth. And a 1 megahertz bandwidth. What is the level of thermal noise that can be expected at the receiver's output? What is the level of thermal noise that can be expected at the receiver's output. Let me repeat. Assume that the mobile receiver has an effective noise temperature of 180 degrees Kelvin, capital K, and a 1 megahertz bandwidth. What is the level of thermal noise that can be expected at the receiver's output?
One more time, please.
Again?
Yes.
Assume that the mobile receiver has an effective noise temperature of 180 degrees Kelvin and a 1 megahertz bandwidth. What is the level of thermal noise that can be expected at the receiver's output? All right, number 4. Ignoring any losses or noise other than described above, calculate the carrier signal-to-noise ratio. Calculate the carrier signal-to-noise ratio, capital C divided by capital N, in dB for the base station to mobile link. Ignoring any losses or noise other than described above, calculate the carrier signal-to-noise ratio, C over N, in dB for the base station to mobile link. Assume that the required signal-to-noise ratio, C over N, is 10 dB. Assume that the required signal-to-noise ratio is 10 dB. Calculate the link margin. Calculate the link margin. Is there enough link margin for satisfactory performance? Is there enough link margin for satisfactory performance? Explain. I'm going to repeat this. Ignoring any losses or noise other than described above, calculate the carrier's signal-to-noise ratio, C over N, in dB for the base station to mobile link. Assume that the required signal-to-noise ratio, C over N, is 10 dB. Calculate the link margin. Is there enough link margin for satisfactory performance? Explain. And the last of the 5 questions. If 9600 bits per second is the maximum data rate that can be transmitted over a channel 200 kilohertz wide, if 9600 bits per second is the maximum data rate that can be transmitted over a channel 200 kilohertz wide, what is the channel's spectral efficiency? What is the channel's spectral efficiency? If 9600 bits per second is the maximum data rate that can be transmitted over a channel 200 kilohertz wide, what is the channel's spectral efficiency?
Spectral efficiency?
Spectral efficiency. Remember we talked about that? That's a way of measuring performance. All right, here is what I suggest we do. I mean, we've got 20 minutes. I suggest we begin at the beginning, and we can proceed in any number of ways. Right? One way we can do it is we can do 1, and then we can do 2, and then we can do 3, and then we can do 4, and we can do 5. Or you can go through and think about what it is that we're going to do, how you would proceed, and then we can go over 1 and 2 and 3. How would you prefer? I don't care.
We just walk through it and do it as a class.
You want to go through the 5 of them?
Yeah.
All right, why don't you go through the 5? Think it through, and then we'll go through it. And you'll tell me. You'll tell me how you did it. I'm not going to tell you. You tell me. I'd like you to think it through. Where I am.
We should work as a class.
Go ahead. No. Do it individually. There's no reason. When you take the exam, it's not going to be a group exam. Right? You're not going to look at reading. He's got his own problems. You don't want his problems.
We should turn it to a group exam.
Go through. Think about it. Think it through. Think it through. Otherwise, I don't know if, and you don't know what you understand and what you don't understand.
Starving, you haven't eaten anything today.
Cellular, radio link, 807 compare it.
What was that width that you questioned for? You said like 200 or 300 something?
200 kilohertz.
Four, ignoring any losses or noise, is that what you're talking about?
200
You
kilohertz.
said something about the transmission size.
Five.
No, it's five. Why do not go together?
5 is 9,600 bits per second is the maximum data rate. That can be transmitted over channel 200 kilohertz wide. What is the channel spectrum?
There's a video.
Is that in the book, sir? Which book is that?
Which book? In a lot of different books. Oh, this is mine. Oh, I made this up.
Let me take a picture.
I think this is based upon one of my old midterms. The only one you can ask questions of is Monica.
What? Can I see your paper?
Can we see it? See if we just wrote down the question?
No, yeah, I want to double check question 3.
Because it's a
3
little...
is
Oh, I'm sorry, 2.
2, ignoring all losses except the losses described above.
No, the one compare cellular radio link A given above with.
That's 1.
Oh.
Compare cellular radio link A given above with an amp cellular radio link B with an 830 megahertz carrier frequency for mobile to base station and an 870 megahertz carrier frequency for base station
Does
to
that
mobile.
paper have the answers as well?
Which of the 2 cellular radio links has the longer mobile to base station carrier wavelength? How much longer is it?
Does that paper have answers on that as well?
What's that one?
Does that paper have answers on that as well?
Oh, that paper, yes, it has answers.
Oh, okay. Well, if it didn't, I was just going to ask, can we see it to make sure we type it correctly? Because it's a little hard to follow along. Accuracy is key, you know. You just don't know detail.
Students that took this midterm didn't have the benefit of the previous midterm. The benefit of going over previous midterms. So you guys are in somewhat better shape, better condition than they're in.
That's because you like us.
That's right, I do. What can I say?
It's okay.
It really isn't difficult. You know, if you've been following along, and if you go back and check your notes, you'll see that it's really quite logical, and I think you should be able to do it. But I want you to think it through before we start going over. Let's talk about question 1. Okay, we've got A, we have link A, and we have link B. Obviously, they're different in terms of the carrier frequencies. And the question is, which of the two is longer mobile to base station carrier frequency? How do you find wavelength? We had a formula. What formula would you use in order to determine wavelength?
C over F.
That's correct. Lambda is equal to C over F. So what would you do here? C is not going to change. Right? C is the speed of light. So the only thing that's going to change is the F. And what we're looking at is mobile to base station. Mobile to base station. What in A, radio link A, what is the mobile to base station frequency?
Can you repeat the question?
In A, carrier link A, what is the mobile to base station carrier frequency?
950?
No.
905.
905. You have to read carefully. Mobile to base station is 905 megahertz. All right, so we would plug that in to the lambda equals C over F. How about B? What is the mobile to base station frequency there?
830.
830. We plug that in. Okay. In both cases, right, you plug it into the formula, lambda equals to C over F. And, you can work out the details. It's not very difficult to work it out. But you will find that, you should find, that lambda B is greater than lambda A. It's just solve the formula. It's not just a couple of calculations. Let's look at number 2. It says, ignoring all losses except the losses described above, calculate the signal carrier level C at the mobile in both dB, W, and watts. Now, what does this sound like? What kind of problem is this one? This is the link one, right? This is one where you have to go through and you have to look at the transmitter all the way down to the receiver. So you have to look at all the parts. All right? What is the transmitter power? Remember, the signal power at the transmitter is what here?
Wait, which one? The mobile or base station?
We're looking at the carrier. It says calculate the carrier, signal carrier level C at the mobile. So what is the transmitter power?
4.
signal carrier level C. It's the receiver. The mobile is the receiver. Remember, C is the carrier at the receiver. So actually the transmitter power is 50 watts. 50. Okay? The base station, it's the base station transmitter. The base station transmitter power is 50 watts. So that's what the transmitted signal power. Then we look at the next step, and the next step is the line loss. What would be the line loss from the transmitter to the transmitting antenna? Or in other words, the gain. What would be the gain from the transmitter to the transmitting antenna? If you know that the signal energy at the base station transmitter is twice that at the base station antenna, what would the gain be over that link between the transmitter and the transmitting antenna? It says here that the energy at the transmitter is twice that at the antenna. So what would the gain be between the antenna and between the transmitter and the antenna? 1/2, right? It would be 1/2. Remember, the gain is the signal output divided by the signal input. And if the signal output is twice that of the signal input, then the gain is 1/2. Make sense? Okay. Let's go on to the next step. Do you remember the next step? We went through this. Susan was talking. The next step is the transmitting antenna. So what is the gain of the transmitting antenna?
dB.
No, it's a transmitting antenna. Remember, we're transmitting from the base station. So assume the mobile and base station antennas are used for both transmission and reception, and their gains are 20 dB and 40 dB respectively. That means the base station is 40 dB. All right. So, but remember, you can't use dB in that formula. You have to convert it to absolute terms. If you're going to use the formula I gave you, the gain thing where you just multiply the gains. So what would the gain be in absolute terms if it's 40 dB in logarithmic terms? 40 dB is equivalent to what? 10 to the 4. 10 to the 40 dB is equivalent to 10 to the 4th. In fact, we looked at this the other day. 40 dB is equivalent to 10 to the 4th. So you'd have to multiply 10 to the 4th. Remember, you're multiplying gains. And this gain for the transmitting antenna is 10 to the 4th. All right, the next gain that we have to look at is the free space gain, or loss. And you know how to do that one. Remember the formula for free space. The thing with the 4 pi d's. Right, so you're going to plug in there, multiply that, and you have to put in the lambda. You have to use the right lambda. And we were dealing with a 950 megahertz frequency. And what is the distance that you would plug into that formula?
10 kilometers.
And that is equal to
10,000.
and I just noticed a mistake. it would be what? What would the D be? 10 to the 4th, right? 10 kilometers is 10 times 1,000. So it'd be 10 meters. All right, 10 kilometers is 10 to the 4th. All right, so you plug all that in. The next block is the receiving antenna. Receiving antenna. And you remember the receiving antenna here is, it's a mobile antenna, it's 20 dB. What would 20 dB do in absolute terms in gain?
10 to the second.
By 10 squared. That's correct. It would be 10 squared. And then the next block, you have to multiply the gain, is the transmission line between the receiving antenna and the receiver. And what would that gain be?
20.
No. Remember it says, assume that the signal energy at the base station... Oh, I guess I didn't specify. Oh, if I didn't, and I didn't. So you would have to assume that there is no loss. You have to assume then, because we said all losses except those described above. We didn't talk about any signal loss at the receiving end. So the gain would be 1. Since we ignore that, any loss, we just have to assume the gain is 1. If I had said the signal energy at the base station and mobile, then you would have to multiply by a hat, but I didn't. I didn't say anything about it. So we have to assume that there is no loss. The gain is 1. Okay? So when you multiply it out, 50 by 1/2, by 10 to the 4th, by 10 squared, by all of that I told you about, I respaced it. That will give you the C. Bernard, do you have a question?
No, that's
All right, so that gives you the C in watts. How do you go from watts to dBW? 10 log to the base 10 of that value. So if you take 10 log to the base 10 of what you calculate here at C, that gives you the answer in dBW. Make sense? Make sense? dBW is 10 log to the base 10 of the watts. That's the definition of dBW. It's really 10 log to the base 10 of the whatever in watts divided by 1 watt, but we saw it was equivalent to the we're running out. Here's a suggestion I'm going to make. We're going to go through this. I want you to think about it. Before the midterm is not going to last 2 hours. Before the midterm, I'll answer any questions you have about this, just to make sure everybody is in sync.
Could you post that?
No, I don't want to post. But let's. I really don't have much more, Bernard, than what I'm saying. I haven't done all the calculations. But let's go. Let me continue to go through, and then we'll figure. 3. It says, assume the mobile receiver has an effective noise temperature of 180 degrees Kelvin and a 1 megahertz bandwidth. What is the level of thermal noise that can be expected of the receiver's output? Now, what formula are you going to use for this, for thermal noise? If you go back to your notes, you'll see there is a formula for thermal noise in terms of the temperature and the bandwidth. N equals minus 228.6. You see that one? dBW plus 10 log to the base 10. It's also in the overhead. So what would you plug in where? That formula requires the temperature. What temperature would you plug in there? 180. And that formula requires the bandwidth. What would you plug in for the bandwidth? Yeah, 10 to the 6. All right, let's do 4. Let's do 4. It says, ignoring any losses or noise other than described above, calculate the carrier signal-to-noise ratio, C over N and dB, for the base station to mobile link, assume the required blah, blah, blah. Calculate the link margin. Is there enough for satisfactory? How do you calculate link margin? Remember I told you. Link margin. Remember, the link margin is the difference between the received signal-to-noise ratio and the required signal-to-noise ratio. The difference between the received signal-to-noise ratio and the required. What is the required signal-to-noise ratio? That's given to you. From the problem statement, it's 10 dB. But it's 10 dB, and you know what that is. It's 10. In other words, an absolute. The received is something you are going to calculate in question 3. The difference is the link margin. The difference is the link margin. And we know that in order for satisfactory performance, this has to be bigger.
This has to be what?
Bigger. Bigger. He says the received has to be greater than the required. So you're going to calculate the received in question 3. You're going to subtract off the required 10 dB, and you're going to find out if that's positive or negative. Clearly, if it's positive, you're in business. Satisfactory. If it's not, then you got a problem. And then finally 5, that's quite easy. Let's do 5. If 9600 bits per second is the maximum data rate that can be transmitted over a channel 200 kilohertz wide, what is the channel spectral efficiency? What formula are you going to use for that? It'll be the one I just gave you. Yeah, it's the one where you divide the data rate by the bandwidth. And the data rate here is what? 9600 bits per second. And the bandwidth is 200 kilohertz. So that fraction measured in bits per second per hertz is the spectral efficiency. The units of bits per second divided by hertz.
The number 5 is kilohertz?
Yeah, it's
200 kilohertz.
200 kilohertz. So that would be 200 times 10 cubed. That would be the spectral efficiency. We've got a little bit of time. I'll be glad to answer any questions anybody has at this point. I'll be around tomorrow also in the afternoon.
So,
What?
would it be possible for you to tell us which specific formula you use over, or
Yeah. In which question?
like anything that we need for the midterm, sure? Like which formula?
Oh, which formula you're going to need for the midterm? One of the formulas on your formula sheet. I can't tell you which specific formula, but I'll tell you this: if you know this, you're in good shape for the calculation.
All of them in good shape.
Yeah, you know these are. I'm not going to ask you a heck of a lot more than them. I may ask you one or two more, but if you, this is the crux. This is the crux of what it is. If you understand the process, and it all really boils down to that, that block diagram. You understand the block diagram? These little wrinkles about link margin, but that's not anything major. You're in great shape. Yeah.
What does the C and the N stand for the
C
link
is
margin?
the signal. It's another way of representing the carrier signal.
And how about the N?
N is just the noise, the thermal noise. And you calculate the thermal noise, and we calculated that.
Yeah, I have that.
So, I'll be around for a while tomorrow afternoon in my office. And as I said, I'll be around after class too, but we can go over it before the midterm.
For the formula sheet, you said only formulas and no words?
Yeah, and I did formula. I mean, the formula sheet is formula.
Can we actually title the formula as in the context? So we know what the context of the formula is for?
So yes.
It's like bandwidth.
It's like bandwidth formula, thermal formula, something like that.
It's okay, right?
Yes.
Yep. Yeah.
Yeah, it's okay. It's okay.
I mean, how can I disappoint you? Yes, you can.
We have to give you the puppy dog eyes out of you. No.
Monica gave him the they always wish to do it.
Yeah, as I said, I'll be around. I've got a class at 6, but I'm not going anywhere for the next hour if you want to come by. We can do that.
Yeah. I didn't get all the questions. Yeah, I got the formulas.
Stop the record.
Ah, formulas.
You know, that stuff down.